Hello everyone, welcome to AIATS Plus Phase 2 discussion. This is slot 2 and we would be taking this discussion forward. So just now Puneet sir had taken over the session and now I would be taking it over. Okay, so let's begin. What are the topics that we have at our disposal? First, see here, see the list of topics. Right, the first two topics are from your 12th class and also the last two topics, right? So pay close attention to them. There are some really very good problems in them, so we will be covering it as well. Alright, see here, ray optics, prism we would be covering, right? So let's say we have a prism. This is a very general diagram of the prism, alright? We have an incident ray that has already been drawn. Then this ray, what do we call it? The refracted ray, right? Why? Because this ray has already entered, isn't it? Then what would happen? This ray would emerge from the other side of the prism, isn't it? So it should emerge. It should emerge something like this, right? Something like this. And we can draw normal at both the surfaces of the prism, right? So see how I am drawing the normal. This is normal at this surface and I am also drawing normal at this surface, right? So this one is your incident ray, refracted ray, and then your emergent ray, right? And what do we call this angle? The angle between the incident ray and the normal, we call it as angle of incidence, I. Then this angle, refracted ray and normal, this we call it as R1. This would be your R2. And this one will be your emergent angle, right? Or angle of emergence, angle between the emergent ray and the normal. And see here, what about this angle? This we call it as A, right? And A is your refracting angle, right? And also remember, this is, as I said in the beginning, this is a general diagram, which means this won't be always the case, right? Wherein the refracted ray is always parallel to the base of the prism. That won't be the case always, right? So this is a general case, right? So we can remember, so at the condition of, this is a point that I want to discuss, at the condition of minimum deviation, right? The refracted ray will be parallel to base of prism, right? In that condition only. Why? Why is so? That is because at this condition, right? At this minimum deviation condition, a few things will happen. Number one, this I will be equal to E, right? At that condition, I will be equal to E and both of these angles would also be same. That is R1 equal to R2, right? But anyway, our topic of discussion is not about this one. We are going to discuss something else, right? Which is, see here, let's say I want to find this deviation. How much is the angle of deviation? What do I have to do? I have to, let's say, extend this incident ray and extend this emergent ray backwards, right? So what does that mean? Angle of deviation means how much the incident ray has deviated, right? So this was supposed to be the incident ray, but in the end, this was the emergent ray. So how much it has deviated, right? How much it has deviated? I can draw it as like this. See, this angle, this one is delta. That is, this much as it has deviated, right? And if you see, this angle I and this whole angle should be equal, right? So that means how much will be this angle? I1 minus R1, isn't it? This should be I1 minus R1, right? And what about this angle? Okay, this was I1 minus R1. What about this angle? It should be E minus R2, right? Because if this is E, this angle should also be E. So E minus R2 will give you this angle, right? And what about this delta? See here, if you see this triangle carefully, right? So let me draw this triangle for you guys. If you see this triangle, this delta is the external angle for this triangle, right? So delta would be nothing but sum of these two interior angles. So I1 minus R1 plus E minus R2, right? So therefore, this angle of deviation, right, delta would become I1 minus R1 plus E minus R2, E minus R2. Now, see here, if you see the original triangle, before I drew this one, right, how was the triangle looking like? See here, this was your angle A, right, and you see, right, this was your R1 and this was your R2, right, this was your R2. So can you tell me a connection between A, R1 and R2? Can you tell me? Because see here, what would be this angle? Can you tell me? What would be this angle? And remember, this derivation is very important from your board exam point of view also. And that way, when you remember the derivation, you would be able to solve the numericals quicker, right? So if you see, this dotted line was nothing but your normal, right? Let me write it for you guys. This was your normal, isn't it? This was your normal. Normal means it is perpendicular to the surface, right? So if this is the surface, this is the normal, and this angle is R1. So what would be this one? 90 degree minus R1, right? And similarly, this angle would be 90 degree minus R2, right? This is 90 degree minus R1, right? And this is a triangle, so if you sum all these three angles, it would sum up to 180 degree. So A plus 90 degree minus R1 plus 90 degree minus R2, it would become 180 degree, right? So that means if you simplify 90 degree minus R1 plus 90 degree minus R2 plus A, this becomes how much? This becomes 180 degree, right? And 90 plus 90 is 180, so it will get cancelled. So what does A become? A is nothing but R1 plus R2. A is R1 plus R2, which means we have derived a formula for delta, which is deviation, right? So angle of deviation, what does it become? See, I plus E, right? I plus E minus R1 plus R2. And R1 plus R2 was A. Okay, minus R1 plus R2, which is your A. So please remember this formula when we go to the next question. And also, as I said, at the condition of minimum deviation, this I and E will become equal, and R1 and R2 will also become equal. See here, see this diagram, it clearly says, right? So at any other delta, right, at any other deviation, you will have two angles, I1 and I2, which means if this is I, that will be E, or if this is E, that will be I. But there is one particular delta at which there is only one angle of incidence that is possible, which means at this angle, we say I is equal to E. Okay, I is equal to E at delta minimum. So please remember that point. All right, very well. See this question. They have said refracting angle 30 degree, which means this is your A, right? And then ray of light incident at 60 degree, which means this is your I or I1, we can say, on one refracting surface, suffers a net deviation of 30 degree, and this becomes your delta, right? And angle of emergence, E they are asking, right? So what is the formula we will use? That same formula, which is delta is equal to I plus E minus A. So delta is how much? 30 degree is equal to I is how much? 60 degree plus E, we don't know, minus A. A is your refracting angle, right? You see the diagram. This was A. A is your refracting angle. And A is how much? 30 degree. Right? So this the minus 30 comes over there, becomes 60. 60 and 60 will get cancelled. So from here you are getting E is equal to 0. So what does this mean, E equal to 0? That means the emergent ray is making 0 degree with the normal. That means emergent ray is emerging at an angle of 90 degree with the surface. Okay. Very well. Now see this question. Two plane mirrors are given, one parallel to the other, and they are separated by a distance of 2 centimeter. And what is the length of the plane mirror? That is also given, right? The length of each plane mirror is 2 meter. And light is reflected at an angle of 45 degree from the edge. So let's say it is incident like this at this edge, and it is reflecting, right? So here we are talking about reflection. So you need to remember the two laws of reflection, which were the angle of incidence is equal to angle of reflection, and the incident ray, the reflected ray and the normal, they will lie on the same plane, right? So if you see, right, so let me draw another diagram for you guys. It was like this, wasn't it? It was incident like this, right? And it is emerging from here like this. And this angle was 45 degree, right? And if you see, this becomes a full triangle. This is 90 degree, and if you want, I can erase this one, right, for better understanding. And this distance was how much? 2 centimeter. And let's say this is how much? This is x, right? This is x. Now, if you consider this triangle, right, just consider this triangle. See here, this is a right angle triangle, and angle, one angle is given 45 degree. So we can take tan of it, right? Tan 45, what would that be? See here, tan 45 degree is equal to perpendicular upon base. So x upon 2, x upon 2. Tan 45 is 1, so x would become 2 centimeter only, right? So what does that mean exactly? That means after one reflection, it is getting reflected for the first time at this point. After one reflection, it will travel 2 centimeter before it gets reflected the second time over here, right? So if I can summarize over here itself, right? So after one reflection, it travels 2 centimeter before it gets reflected the second time. So let's say it suffers n reflections. N reflections, and how much distance it has to cover along the horizontal? It has to cover how much? 2 meter, right? The entire length of the mirror has to be covered. So it has to cover 2 meter. 2 meter means how much? 200 centimeter. So how many reflections has to happen? Pretty simple, right? Simple unitary method. We have to divide it 200 by 2. So n is nothing but 200 by 2. That's it. You got the answer. 200 by 2. That is 100. Okay. That is 100. So 100 is the answer. So little bit of trigonometry we had to use. So this is basic trigonometry you need to know. That would be enough. All right, very well. Moving on. The next topic is from your telescopes, right? Telescope, simple microscope and compound microscope portion of the ray optics chapter. That is also very important. Optical instruments, right? So that topic is also very important, right? So we are talking about compound microscope, right? And in compound microscope, how many lenses do you have? You have 2 lenses, right? Yeah, good morning. Good morning, Mukesh. All right, very well. See here, you have 2 lenses, right? Objective lens, and you have the eyepiece lens. And remember, both of them are convex lenses, right? And what is the final purpose of using this optical instrument? It is to obtain a magnified image, right? We don't want to obtain a, let's say, diminished image, right? What's the purpose of that? So we want to obtain a magnified image. That's why we are using 2 convex lenses. so that the magnification will be even higher, right? So this convex lens, objective lens, right, it will have, you can remove like this, small focal length, right, small focal length. And obviously if focal length is small, what does that mean? The lens is also small and the aperture, right, so small aperture, right, small aperture, whereas for the eyepiece it is the reverse, right? So you can say it is large focal length, right, and we have large aperture. And how are the images formed? This also you need to remember, right? The ray diagrams. So the objective lens, it forms a real, inverted and magnified image. Real, inverted and magnified image, right? I can write like this, forms A. And what about this one? This also forms a magnified image, so it will magnify this magnified image. It will magnify it even further. So you can write this forms a virtual, erect and magnified image, right? Virtual, erect and magnified image, right? And since we are speaking of magnification, what is the formula for magnification of, good morning Shrishti. So since we are speaking of magnification, right, so what is the formula for magnification of this objective lens? The same formula we will use for any convex lens, right, which is the distance of the image upon the distance of the object, using in terms of sign convention, right? So we can express like this, V naught by U naught. You have to use the appropriate sign convention, whether it's positive or negative, you will fill these values. And similarly for eyepiece, the magnification will be V by U, which is image of eyepiece upon object distance of eyepiece, right? Now see the diagram. This is what we have done, isn't it? See here, as I said, the objective is small focal length and small aperture. See, it's a small lens, whereas this eyepiece is even much bigger, right? It is literally going outside the screen, that much bigger it is. And see, a real inverted image is formed, magnified, and what is the eyepiece doing? See, it is forming even a further magnified image, right? So this one we would say is virtual, erect and magnified, isn't it? It is erect with respect to, this is the object for the eyepiece, isn't it? So virtual, erect and magnified, right? And these are, remember, this is the object distance U naught, this is the image distance V naught for the objective lens, and this one, this distance, right, this distance would become object distance for eyepiece, and from here to there would become image distance for eyepiece, right? See the question, that the question we have not yet done, right? See here, magnifying power of microscope is given. So compound microscopes, magnifying power they have given, right? So magnifying power of compound microscope is 80. In terms of eyepiece and objective, what can we write it as? It becomes magnifying power of objective into magnifying power of eyepiece. Simple multiplication, right? So that means 80 is equal to, right? And also remember, if these values V naught and U naught are given, then also you can find the magnifying power of objective, right? But anyway, they have already given magnifying power of eyepiece. So M naught into 5. So what would be M naught over here? 80 divided by 5, right? 80 divided by 5. That's it. So the answer would be 16. The answer would be 16. Very well. So I hope you found this discussion interesting, right? Regarding compound microscope, and you have to please practice them, these diagrams on pen and paper, right? Please practice them. Very well. Now we are moving to the next topic of 12th class, right? Magnetism and matter. See here and see this question, what is written here. The magnitude of magnetic induction, and this we are denoting it by symbol capital B, all right, and magnetizing field intensity, this we will denote it by the symbol capital H, right. In a sample of magnetic material are given as B and H, and the magnetic susceptibility of the material they are asking. So magnetic susceptibility, please remember, that is given by the symbol Xi, right. Xi, and Xi depends on what? It depends on the ability of that material, this magnetic material, to be magnetized by the external magnetic field. It depends on the ability. And then you have another thing given, that is mu naught, which is permeability of free space. So all these things I have labeled and written the symbols. And what are they asking us to find? They are asking us to find Xi in terms of other things, right. So before this, let's discuss some theory regarding them, right. So remember, so let's say for example we have a long solenoid, right, a long solenoid of n turns per unit length, right. This is a long solenoid, okay. I'm drawing a rough diagram. So it has n turns per unit length, right, and let's say it is carrying current I, right. Current I is in this solenoid. So let's say current I is flowing, right. So what can you tell me the magnetic field? Will there be a magnetic field inside the solenoid? Yes, obviously, right. There will be a magnetic field that will flow inside the solenoid. It's a long solenoid, right. So we can say that the magnetic field inside is uniform, and the magnetic field inside, we can write it as what exactly? We will write it as, let's say, B naught, right. B naught will be equal to mu naught n I. Mu naught you already know what it was, I told you over there, n and I, right. And this we can also write it by another symbol, which is mu naught into H, mu naught into H. And what was H exactly? See the question again. H is your magnetizing field intensity, okay. And this is the intensity which you are having before this material is inserted, right. We are inserting a material, right. See, in a sample of, and see now what I am doing. Now I am inserting a material in the solenoid, okay. So let me write like this. So with material, what happens? With material, this material will also contribute a magnetic field of its own. So now what will be the magnetic field inside the solenoid? See how I am doing? This will become B naught plus Bm. Bm is the magnetic field contributed by the core of the material, right. So Bm, okay. And this B naught is equal to what exactly, right. So if you want, I can write it over here. This B naught is your mu naught into H, right. And this Bm, right, this Bm you can write it as mu naught into M, okay. Bm, M. And what is this M? M is the magnetization of this material, okay. And H you already know what it is. So this you can write it as what exactly? You just substitute them over here. So this becomes mu naught times H plus M, right, H plus M. Now if you see, there is a connection between them as well, right, because this H was of the solenoid when there was no material, and this M belongs to the material, right. This is due to the material. So can there be a connection between them? Yes, there is, right. So this M is also related to this H. We say M is proportional to H, okay. So we say M is equal to Xi H, okay. M is equal to Xi H. Xi, what is it? That is also, Xi is also written over there, right. Susceptibility of this material, right. I already told you what this magnetic susceptibility is. And so you have to substitute over here. So what will it become? See, mu naught into H plus Xi H, H you can take it as common. So it becomes mu naught into 1 plus xi into H, and 1 plus xi becomes your mu r, that is relative magnetic permeability. Okay. And what becomes mu naught into mu r? That becomes magnetic permeability. So please remember the difference between these terms. Mu naught was your what? Permeability of free space. This is relative permeability, and this one is magnetic permeability. Okay. And this is your B. If you simply want, you can just, this is your B only. So instead of B naught here, this is B. So B is equal to mu H, and M is equal to xi H. That you need to remember, right? M is equal to xi H. Very well. Now come here, what they are asking in the question. Xi you have to represent in terms of other things, isn't it? So M was what exactly? M was xi H, and what was B? B we wrote it as what? Mu naught into H plus M, isn't it? So mu naught into H plus M, right? B we know, mu naught we know, H we know. Why I am saying we know? Because it is given in the question, right? M we don't know. So we have to eliminate this M. So what do we have to do? Bring all these terms to this side, right? So what does it become? B by mu naught is equal to H plus M, right? And then bring this H to this side. So therefore M becomes B by mu naught minus H, right? But we were supposed to find xi, and what was xi? Xi is M by H, isn't it? Xi is M by H. So divide this by H again. Divide it, you will get xi. Xi is equal to M by H. So divide it by H, so it becomes 1 by H. Right? Check the answers, which one it should be. Xi, right? So if you solve it, you will get B by mu naught H minus 1, right? B by mu naught H minus 1. All right, very well. All right. So let's move to our next topic, right, which is waves, right? And waves, for this, this belongs in your 11th class, okay, and it's a very interesting topic, just like the oscillations chapter, right? And what is the speed of wave given here? See, speed of wave is given as 360 meter per second. We will denote it by the symbol V, and the frequency is also given, right? We will denote it by the symbol F, right? Wavelength is not given, isn't it? Frequency is given, right? So we can find the wavelength, isn't it? So if velocity of wave is given, frequency is given, we can find the wavelength, right? And they are asking path difference, they are asking, and phase difference, it is already given, right? So for example, let's say this is the wave, right? The wave, and what is wavelength? Wavelength is distance between, let's say, two crests or two troughs, right? So this is your wavelength, and let's say this wave is propagating towards right, okay? So let's say this wave is moving, right, moving along positive x-axis, right? So it is moving like this, isn't it? So what can we write the equation of this wave as, right? Remember, this is your y-axis, this is your x-axis, right? And remember, this wave has multiple particles and the displacement of this particle, right? So let's say this y coordinate I am talking about, right? This is the y coordinate. This y coordinate will be different for each particle at the same time and at a different x. So the equation of wave depends on both position and time. So I can write y is equal to a sine omega t minus kx. Okay, omega t minus kx, because this wave is moving in positive x direction. Okay. Very well. And what is omega here? Omega is your angular frequency, right? And what is k here? K is your angular wave number, right? These notations you need to know. And what is this term in total? What is it called as? Right? We can call it as, right? We can call it as what? The phase of that wave, right? The phase of wave, right? The phase of wave. And as I said, this wave, this photo of this wave has been drawn at a particular time, right? If you change the time, let's say it is drawn at t equal to 0 second. After some time, 1 second or 2 seconds, this wave will move, right? So it depends on both time and x. Now come back to the question, what it's saying, right? Velocity and frequency are given, right? And you know the relation between them, v is equal to f lambda, isn't it? So lambda we can find speed by frequency, right? So lambda becomes speed by frequency. Speed was how much? 360. Frequency was 500. So this becomes how much? 18 by 25, right? In meter, isn't it? Because the SI unit of wavelength will be in meter. All right. Now see what they are saying. Phase difference is 60 degree. Now if you remember, what did I draw the phase as? This is the phase, right? And 60 degree it is given. And you have to represent it in terms of radian, right? 60 degree will be how much radian? Right? So let me draw it like this. So phase difference, it will be delta phi, right? So I can write it like this, phi 2 minus phi 1, right? And phi was this omega t minus kx, isn't it? So this becomes omega t minus kx2, right? Omega t minus kx for this particle and omega t minus kx for the next particle, right? Kx1. Now you can ask the question, well, what about time? Why have I written not t2 and t1? Because both of those particles we are considering at the same time. So t will remain the same, right? So if you solve, what does it become? See, it becomes k into difference between the both x's. So can I write it like this? Delta x, right? And this is your delta phi, right? And what is delta phi given here? 60 degree. 60 degree means pi by 3. So it becomes 3 by 25, isn't it? 3 by 25 in meter, right? Because lambda we wrote in meter. And 3 meter is how much? 300 centimeter. So 300 by 25, right? So 3 into 100 by 25, that is 3 into 4 only. And 3 into 4 is how much? 12 centimeter, right? So there goes your answer for this one, 12 centimeter. All right, very well. The next topic from your 11th class, right? I deliberately placed this topic after the previous topic, right? Waves. Why? Is because, see, for the waves, we had written y equal to a sine omega t minus kx, right? Because the position of each particle depends on x and depends on time. But here if you see, SHM of a particle, right? Let's say SHM of the particle that is oscillating around x-axis, right? It can be expressed as what? We will write it as a sine, we won't write omega t minus kx. We will simply write a sine omega t. A sine omega t, right? Because the x, the particle is varying along x-axis or oscillating along x-axis. The position is varying as this, right? So x is equal to a sine omega t. So superposition, so let's say we have one particle, right? So let's say this is particle 1, okay, and it is oscillating or it is undergoing SHM with amplitude a1, and and we have another particle 2. It is oscillating with amplitude A2, A sine, let's say, omega t plus phi, So what does this mean? Phi is a constant, right? Phi is a constant, and here the same terminology we will use which we used over there, right? Which is, what is the phase of this SHM? Omega t. What is the phase of this SHM? Omega t plus phi. So what will be the phase difference? Phase difference will be omega t plus phi minus omega t, which is phi only. So phi is the phase difference. All right. Phi is your phase difference. Very well. So let's see what the question entails for this one, right? And I have also written superposition. Superposition means what? Both SHMs, they are superposing on each other, which means you will get a resultant SHM, right? And the resultant SHM will have a different amplitude, but one thing will remain the same. And what is that thing? That thing will be this omega, right? Because the angular frequency is remaining the same. And if angular frequency is same, the time period will be same or not? Because the time period formula is what? 2 pi by omega. So if omega is same, the time period of both SHMs is also same, but the amplitude will be different. Okay. So let's see what the question is asking us. See here, they've already said executing SHM in same direction is also given. Same direction means if this particle is going oscillating like this, other particle is also oscillating like this. And same amplitude, let's say amplitude is A, and same time period. That means T1 equal to T2, that means 2 pi by omega 1 equal to 2 pi by omega 2. That means their omega is also same. But phase difference is given. So phase difference was what over there? Phase difference was phi only, right? So phi is given as how much? 2 pi by 3. Amplitude is A, angular frequency is omega, right? Energy of oscillation is also given, and what was the energy of oscillation in an SHM? What was it? Let's say a spring, right? A spring is oscillating with a block attached at the other end. What was the total energy of oscillation? It was coming as half k into a square, right? Half k into a square, where k is the spring constant. But the energy is proportional to amplitude square. That's what I'm trying to stress on over here. So the energy will be proportional to amplitude square. Okay. So for both these waves, we can say E is proportional to a square, right? So let me just write it down for now. Okay. Yeah, I hope you can hear me clearly, right? I hope. Very well. Now see here. So superposition takes place, and you have to find the resultant amplitude, right? How will we find the resultant amplitude? Because remember, both have the same amplitude, A1, A2 is equal to A only, right? So what we have to do? A1 square plus A2 square plus 2A1, A2 cos phi, right? So 2A1 into A2 cos phi. So cos phi is how much? 2 pi by 3 is how much? 180 by 3 into 2. So 120 degree, right? It is 120 degree. Okay. And how much is cos 120? Can you tell me? Cos 120 is how much? Let's calculate if you want. Cos 120 is your cos 90 plus 30, right? Okay, very well. Cos 90, okay, I'll write it like this. Cos 90 plus 30 degree. 90 plus 30 means second quadrant. So cos will become sine, but with a minus sign, because cos is negative in that second quadrant. So it will become minus sine 30, right? So minus sine 30 degree, that is minus 1 by 2. Put minus 1 by 2 over here. Put minus 1 by 2 over here. So what does it become? See, minus 1 by 2, 2 will get cancelled. It becomes minus a square. A square minus a square, 0. So this becomes what? Under root of A square only. That is amplitude A, right? So after the superposition, right? So after the superposition of both waves, the resultant amplitude you are getting it as A. All right, very well. Moving on, moving on. See here, they said particle is executing SHM. We are moving on to another question. With time period T, right, and amplitude A, graphical plot of velocity versus displacement they are asking. So velocity versus displacement, right? So what was displacement equal to? Can you tell me? We'll come to the plot. So displacement, we wrote the equation as what? X equal to A sine omega t, isn't it? So from here I can say sine omega t equal to x upon a. And if you differentiate this once, what does that become? Dx by dt, it is particle velocity. So dx by dt, that is v, it becomes what? A omega, sine becomes cos, so cos omega t, right? And from here you get cos omega t equal to v by a omega, right? V by a omega. Now since you have to find the equation between x and v, you have to put them in a proper expression, right? So just square them and add them. What does it become? See, sine square plus cos square. One, sine square theta plus cos square theta. So just put them over here. So it becomes x square by a square plus v square by a square omega square equal to 1. And if you see, this is the equation of ellipse, right? Where x and v are plotted along either of the two axes. See, for example, this is the ellipse, right? Let's say this one is your v and this one is your x, right? And x square by a square, that means this distance, right? This distance would be equal to a. And v square by a square omega square, so this distance would be equal to a omega, all right? And this is your ellipse, right? But what happens, let's say if I put omega equal to 1, right? If omega equal to 1 radian per second, right? Then what happens, see, it becomes x square by a square plus v square by a square equal to 1. So that means it becomes x square plus v square equal to a square, right? So that means if I were to draw over here, right? Let's say this is your x and this is your v. This is the equation of a circle, right? The circle whose radius is a, right? Obviously the units would be different. This is a meter and that is a meter per second, right? So if you come back to this question, what are they saying? The graphical plot of velocity versus displacement, it can be. So it must be a parabola, wrong. It must be a straight line, wrong. It may be a circle, yes it can be, right? When omega equal to 1. It may be a parabola or hyperbola, that's also wrong, right? Very well. Wave optics. So wave optics is a very interesting chapter, and I think this topic was also covered, right, little bit last time previously as well. This is the diagram of let's say for example we have a monochromatic source, light that is coming from a monochromatic source, and it is falling parallelly on this single slit, right, and it will undergo diffraction, right? And in this diffraction we say what is the path difference between the two edges of the slit. So this is the slit we are having, right? This is the single slit, and let's say around this edge the light rays, they will bend, and what will be the path difference between them? It will be equal to a sine theta, right? It will be equal to a sine theta, and this would be equal to n lambda for what exactly? If you remember in Young's double slit, we had written the same expression, but over there we wrote just a minute. Over there we wrote A sin theta equal to n lambda for constructive interference, right? Constructive interference meaning maxima, but here we would write it for minima. Minima meaning the resultant intensity is coming out to be 0. So if you see, this diagram is also drawn for intensity varying with position, right? So at which positions, can you tell me, intensity is 0? Intensity is 0 at this position, this position, this position, isn't it? So for, if you put P equal to 1, that is n equal to 1, the same expression they have written over here also, okay? If you put n equal to 1, what will you get? A sin theta equal to lambda, and remember this theta is very small. Why am I saying this theta is very small? Because see, this is the theta, isn't it? Tan theta would be what? This distance upon this horizontal distance, and horizontal distance is the distance between the slits and the screen, right? This we usually denote it by the symbol capital D, right? Capital D, this you already did in your Young's double slit as well, right? This y upon capital D, and this capital D is given as very, very high. So this tan theta would be very, very low. So if tan theta is low, so we say it is approximately equal to sin theta, or we say it is approximately equal to theta. So tan theta we can write equal to theta equal to y by d, right? So y by d. And what was coming from here? Tan theta equal to, I can approximate sin theta as tan theta, right? So tan theta equal to what? N lambda by A. And tan theta can be written as theta as well, okay? So theta is n lambda by A, and theta is also y by d, right? And this, remember, is for minima, not maxima, for minima. So if you put n equal to 1, first minima, right? So what is y you are getting? Y you are getting it as n lambda d by A, okay, for first minima. Second minima would be n equal to 2, so 2 lambda d by A. So like that you have to go, right? I am not discussing maxima, see why. Let's see the question, right? What's the question they have given? See, wavelength lambda they have given falls from a distant source on a single slit 1 millimeter wide. So this becomes your A, width of the slit, and then the resulting diffraction pattern is observed on a screen 2 meter away, right? This becomes capital D, and as you can see here also, this D is very, very high, isn't it? 2 meter is much, much larger than 1 millimeter. So D is very, very high. So there, in all those cases, tan theta can be approximated as sin theta, approximated as theta. So in all those cases, you can find y also. Y is the distance of first minima from the midpoint, right? The width of central maxima they are asking, right? So width of central maxima, see here, this is your central maxima, isn't it? Width means which distance? This distance, right? Because this was your first minima on this side and on that side. So what will be this distance? This distance was how much? We just found. So if you want, I can write it over here. So y1 is equal to lambda d by A. So lambda d by A plus lambda d by A. So it becomes 2 lambda d by A, right? So this width they are asking, right? Width becomes 2 lambda d by A. So just put the values, simple mathematics. So 2 into 500 nanometer, that means 10 power minus 9 into D. D is how much? 2 meter upon A. A is how much? 1 millimeter. Millimeter means 10 power minus 3, right? Meter. So if you solve it, you will get the answer 2 into 10 power minus 3 meter, right? Because it becomes 2 into 10 power 6 into 10 power minus 9, so meter. So the answer should be 2 millimeter, right? 2 millimeter. And a very similar question I have another as well. See this question, the same stats are given, but here I am asking the distance between the first dark fringe on either side of the central bright fringe. So let's go back to the diagram again. This was the first dark fringe, and this was the another first dark fringe on other side of central bright fringe, right? So what was the distance between them? It was this distance only. So there also the answer should be the same, right? Because the formula should be the same. So there also, for this question, right? For this question also the answer should be 2 millimeter. Okay. You can take this question as your homework, all right, and this question as your homework, and you can check whether you are getting this 3 millimeter as the answer. Very well. Moving to next topic. Okay, so one homework I have given. See this question of polarization, right? Polarization means that, see here, rough diagram, right? So you have an interface separating two media, right? That is air and glass. An incident ray is falling like this, right? An incident ray, we say, is unpolarized. Unpolarized means what? That it is vibrating in all directions, right? So let's say, for example, this is the incident ray. It is moving this way, right? It can vibrate in this way also, right? The particles, or it can vibrate in this way also. It can vibrate in that way also, right? So in all directions it is vibrating. Okay. And what will be the angle of incidence? What do we have to do? We have to draw a normal, isn't it? This. And this will be your angle of incidence, I. And what will happen? Some part will get refracted and some part would get reflected, right? But at a particular I, at a particular angle of incidence, equal to theta p, right? Which is what we call Brewster's angle, right? So what would happen? That the reflected ray would be completely plane polarized. Plane polarized meaning that the particles would be vibrating in one particular direction, right? That's why if you see, I have drawn it like this. One particular direction. It's also written perpendicular to the plane of paper, which means it will be vibrating in this direction only. You won't say it will vibrate in all directions. Okay. And what about the refracted ray? It won't be completely plane polarized, which means there is still some partial polarization is there. Okay. In some books, it's also written unpolarized, which means incident ray is also unpolarized, refracted ray is also unpolarized. That's not true. Little bit of polarization would be there. Okay. So we say at that angle, this would happen. And there is also another condition, right? The angle between reflected ray and the transmitted ray, it should be equal to 90 degree. Okay. It should be equal to 90 degree. So let me draw it like this. So this is your angle of reflection, right? And if this is angle of incidence, it should be equal to angle of reflection. These two angles are same. This is angle of refraction. And what would be this angle? As I said, these two rays have to be perpendicular, right? So this angle has to be 90 degree for this to happen. Okay. For this to happen. And if you see the question, they have clearly said the same thing they have described, and they are asking, see the angle between, see here, the angle between reflected ray and refracted ray, right? So the answer obviously should be 90 degree. The angle will be 90 degree. And another additional information which you can remember is that the mu, right, the angle refractive index of that medium, it would be related how? It would be related as mu is equal to tan of theta p. You can remember this formula as well. Okay, it might come in handy. All right, very well. Moving to the last topic of the day, semiconductors. It's an interesting topic, right? See the question. An ideal diode is connected to an external resistance, right? This is the external resistance, and they have already said ideal diode. So ideal diode, remember, if it is connected in forward biased condition, right? If you want, I can write over here. If it is connected in forward bias, so what would that mean? That the diode is connected like this. Okay, let me draw it over here. So this is the P end of the diode and this is the N end, right? So P has to be connected to the positive end and N has to be connected to the negative end of the circuit, right? So this we call it as positive forward bias, and in forward bias the ideal diode would behave as what? It will behave as a simple wire. So it will offer no resistance whatsoever, right? But what if I reverse it? right? Reverse it like this, see. P here only, N here only, but P is connected to the negative terminal or N is connected to the positive side of the battery or the positive terminal of the battery. Then we won't say it is forward bias, right? Then we will say it is reverse bias. And in such cases, here it was offering 0 resistance. Here it will offer infinite resistance. That will no current will flow. That means we can say it is behaving like an open circuit. Okay. Here like a closed circuit. Now see, come back to this question. They have already said ideal diode, so it offers no resistance, simple wire. That means for this circuit, what is the potential difference? V is equal to 5 volt. Total resistance is how much? 100 ohm. And they are asking the current through the diode, I is equal to what? Use Ohm's law. V is equal to IR, I is equal to V by R. So V by R, 5 by 100, right? So 0.05 ampere, or we can say 50 milliampere. 50 milliampere. And if I had to ask another question, let's say I am connecting this in the reverse way, then it will become reverse bias, right? Then the current would be 0. Then the current would be 0. All right. Very well. Now we have come to the last question of the day, literally. Now see here, a logic gate has been given for this circuit and you have to find the output Y, right? Connections have been drawn like this. And this implies that a battery has been connected over here, or you can say a potential difference has been provided over here. So a battery has been connected, right? So let me draw the truth table first, right? Let's say this is A, this is B, and this is your Y, that is output, right? So let's say I'm leaving A just like it, that, and B also I'm leaving just like that. That means I have not closed them. That means they are remaining open. So we will say the input for A and input for B is 0. Okay. So now just see, this is a circuit and these two wires are open. So will current flow in the circuit? It won't flow, right? So if current is not flowing, there will be no potential drop across this resistance. So that means there will be no output. No output, so 0. Okay, so you can remember like this. Yes meaning 1, no meaning 0. Right? Now, let's say I am closing A. Closing A, right? Closing A like this. So current can flow through this one, and I am not closing B. Now tell me, will current flow here? Yes, it will, right? See, from here current will flow like this. That means there will be a potential drop. That means, will there be an output? Yes, it will. So we say output is 1. Right? Similarly, instead of A, I had closed B. Then what would have happened? Then also current will flow. Then also there would be a potential drop. Or let's say I am closing both switches. Will there be a potential drop? Yes, there will. So output will be 1, right? So what is this similar to? This is similar to which of these gates? You have to tell me, right? So this, remember, is similar to this one, right? That is OR gate, right? OR gate, right? OR gate. This is A, this is B. So 0 or 0 is 0. 1 or 0 means 1. 0 or 1 is 1. So the answer will be OR gate. And you can also remember OR gate like this also. Y is equal to A plus B, right? Y equal to A plus B, 1 plus 0 is 1, 0 plus 1 is 1, like that, right? Now let me give you a homework for you guys. The same circuit I am going to be drawing, right? You see here, this would be homework, right? So let's say I have connected a battery over here. Let's say V1, then resistance R, and here we have the output Y, right? This is switch A, then you have R1, then switch B, then you have R2, right? So comparing both questions, right? Here these resistance, you can say they were connected in parallel, and here these resistance are connected in series. So here you have to tell me this is similar to which gate? This is similar to which gate? So you can try the same method which I did, and it will come out as similar to AND gate, right? So I'm writing the answers as well, okay? So it will be similar to AND gate. All right, students, so very well. So I hope you had a good time, and thank you for watching the session.